And I'm really excited today because actually this is the 10th anniversary of a very simple conversation between two professors here at Forsyth Tech and myself, having coffee, thinking about a lecture series that we could put on. And so we've now had 60 lectures, and we've done it over 10 years, and we've covered a gambit of technology and science. And so I'm really proud of you guys today because it is so nice outside, and I kept on telling Dr. Criswell, we're competing against beautiful weather. But anyways, I'm very, very excited to see you here, and I want to thank Dr. Alice Rudolph-Adams for suggesting Dr. Criswell. We know Dr. Criswell really well. We're really, really pleased that she's here. So I just want to thank you again, and if you ever need to see these lectures, you just need to YouTube. Just search on YouTube. You can pull them up, or you can go to our website, which is very easy to remember, biotechworkforce.org. So I'm going to invite Dr. Rudolph to come up now and introduce our speaker. Thank you.
Yes, we are very pleased to have Dr. Criswell with us today to speak about her interest in her research interest. And I was able to see her at another conference earlier this year and was just so pleased with her talk that I was excited that she agreed to come back and speak again with you all here at Forsyth Tech. So Dr. Tracy Criswell is an assistant professor at the Wake Forest Institute for Regenerative Medicine, we call WFIRM, at Wake Forest School of Medicine. After she received her PhD in cell biology from Case Western Reserve, Dr. Criswell joined the laboratory of Dr. Carlos Arteaga at Vanderbilt University, where she studied the role of TGFβ signaling in breast cancer metastasis. In 2009, she joined WFIRM as a senior research fellow and was promoted to faculty in 2012. Now, as a member of the education committee at WFIRM, Dr. Criswell also plays an active role in educating and mentoring young women and underrepresented minority scientists. She's been a chair of many committees at Wake Forest and in TERMIS, which is Tissue Engineering and Regenerative Medicine International Society. And she's also active in community outreach. Dr. Criswell's research interests focus on identifying new therapies to aid skeletal muscle regeneration after acute and chronic injuries. She developed a novel rodent model of muscle compartment syndrome that has led to several discoveries related to the pathogenesis of muscle injury and consequent regeneration. Today we will hear of her research interest in aging and sex differences in the regenerative process. Now, she loves to have questions, so if you have any questions about any of her research, muscle regeneration, muscle compartment syndrome, aging and sex differences, okay, in the regenerative process, please feel free to ask her any questions that you may have. So I'm going to turn it over to Dr. Tracy Criswell, and thanks again.
Can everybody hear me? I don't know if am I not on?
Try now.
Can you hear me? I speak really loud, so even if the microphone doesn't work, you should hear me. If you can't hear me, start jumping up and down and waving your arms, and I'll speak up a little louder. It works? Okay, perfect. I am very happy to be here today. I am an assistant professor at WFIRM. I've had a kind of a twisting career to get where I am now, which I've learned is really not that unusual. When you're in high school, my daughter just started college, so I just went through this with her, but when you're in high school, I'm gonna do this, and there's gonna be a straight path to this, I'm gonna make lots of money, have a family, or, you know, many dogs, maybe. So when I was in high school, I played the flute, and I said, I was told, not asked, by my teachers that I had to take AP Physics. And I went to my teachers and said, I really don't think I should have to do this. I am never going to be a scientist. I'm a musician. You really don't know everything here in high school. What do you think you might? My parents still hold that over my head, but just once in a while, right? But I do have a degree in music, did that first. Decided that teaching music wasn't for me. I'm a flute player, so there are millions of flute players all over the country, and only a couple of spots in every orchestra. So playing professionally was kind of out of the question. Plus, I had horrible stage fright, so auditioning never went well. Decided didn't like teaching music, went back to school, was going to be a vet. And then someone said, you don't want to be a vet, you want to be an MD. That's where the money is, right? I'm like, yeah, okay, I'll be an MD. Took the MCAT twice, realized it probably wasn't for me, and then I got involved in research, and it clicked. I just knew that that's where I was supposed to be, and I guess the rest is kind of history. I'm going to talk to you today about some things that I'm passionate about. So I wasn't quite sure what to talk about today, and when I had asked a colleague of mine, she said, just talk about what you're passionate about. And so I am passionate about tissue engineering, regenerative medicine, aging, and sex studies. It's personal. I'm an aging woman, so science is personal, right? Let's see. Oh, I have a timer of some sort, or a reminder. Yeah, I might have to go out to get rid of that reminder. Okay, whatever. Did it go away? It did. Okay. Mark Twain is one of my favorite authors. He was sarcastic before sarcastic was a thing, right? Age is an issue of mind over matter. If you don't mind, it doesn't matter, right? Happens to everybody. And it's something we need to, you guys, most of you are pretty young still, the beginning of your lives, beginning of your careers, and you'll be facing the aging process someday as well. I'm going to start with a little I'll get used to this. Start with an introduction to where I work. I work at the Wake Forest Institute for Regenerative Medicine, W-Firm. This is a plaque that's in our building as soon as you walk in the door. This is our mission. Improve patients' lives by developing regenerative medicine, therapies, and support technologies. So we really want to help people get better. That's our goal. There are a lot of us. When I started at W-Firm 10 years ago, we had one floor of our building. Now we have all 4 floors, and there's about 400 employees at W-Firm at any one point in time. And we make up all different kinds of careers. So clinicians, various types of research scientists, be it bachelor's degrees, master's degrees, PhDs, associate degrees, biologists, chemists, you think of it, we got it. We also have vets, because a lot of our studies are done in animals before they go into people. We're educators. One of the pillars of our institute is education. So my boss, Dr. Anthony Atala, puts strong emphasis on educating the next generation of scientists. But not just the next generation of scientists, but also the community on what we do at W-Firm. We're students. The nice thing about being an academic faculty member is that I never stop learning. I'm pretty sure my husband still thinks I don't have a job. I'm just constantly going to college over and over and over. We have lawyers, a lot of intellectual property. So, new technologies that come out of our institute. We have lawyers to help with that. Science advocates. And so anybody interested in science really needs to be an advocate for science. And that can be an advocate to your peers, to politicians, to your church, to your family, at whatever level. But we need to get across our message so people understand what we're doing. Science writers, communication is really, really important when it comes to being a scientist. We have to be able to communicate our ideas to other scientists as well as the lay public. We have grant administrators. These are the people that keep us going, right? They are not secretaries. They are administrators. They deal with the NIH, and if I had to deal with getting these grants in all the time, I probably wouldn't be standing here. I'd probably be working somewhere else right now. And then we also have business executives, because a lot of what we do is tied in and cooperates with companies. So it takes a village to tissue engineer an organ or a tissue. So sex differences in research. I picked this quote from, it's actually a rather obscure paper. It came out in 2017, but I thought it's straight and to the point, right? Being male or female is an important fundamental variable that should be considered when designing and analyzing basic and clinical research. Well, you're probably thinking, well, yeah, right? Of course, we're different. But we didn't always think that way. So before I start talking about our differences, I want to point out our biggest similarity with sex differences. We are males and females, we're both the same species. If you look up sex differences in humans, there are thousands of papers, just thousands of them. But if you look up sex similarities, I couldn't find. I found one, but it had to deal with chakras and things like that. So I think it's very important to emphasize that mostly we're the same, but we do have some differences. So prior to 2014, really in the 1970s, the NIH, which is the National Institute of Health, which is a major funding agency for academic research, the NIH, U.S. Food and Drug Administration, which is the administration that approves new drugs and compounds, recommended against testing drugs on women, and particularly women of childbearing age. Why do you think they said don't test on women? You're probably right. Yeah, that's part of it, yeah.
If they might find out, surprise, they're pregnant, and by the way, the drug affects the baby.
That's part of it too. More basic though. Women's hormones change every month, right? We go through hormonal fluctuations, and it was decided that that would bias the results. They just decided not to include half the population in all these clinical trials. 2014, around 2014, the FDA started to realize that they excluded half the population in all these clinical trials. Maybe that wasn't such a good idea. However, laboratory research, so preclinical research, still primarily relied on male animals to do the testing. And ironically, this imposed a potent biological influence on the very outcomes of interest. If you disregard women because of their hormone cycles, well, how do you know if the hormone cycles are going to have an effect on the drugs women take, right? You don't. 2016, the NIH requires the use of both sexes in preclinical and clinical research. So, 2016, sex as a biological variable became important. So that was 3 years ago, right, that someone said maybe we should include women equally in these studies. Sex is a biological variable. So now when I write a grant, if I want to study just one sex, men or women, I have to justify it, right? Otherwise, I have to include both. Now there's a couple of problems with this. One is that, do I really have to justify sex as a biological variable if I'm studying menopause, right? Well, I do, right? I do still have to do that. The other problem is the NIH just doubled the size of every preclinical experiment that's ever been designed, right? You do it one set of animals, you've got your statistics to back it up, but if you're going to do it in both sexes, you've doubled it now. But they didn't double the money they gave us, right? So yeah. 2016, our government realized that men and women are not the same, and maybe we should test both sexes. So how are we different? This kind of gets to the nature versus nurture argument, right? Are men and women different because of a biological component, or are they different to how they're brought up? Now, I remember when my daughter was little, she was really into Legos, and you go to Target to the Lego section, there were the pink Legos for the girls, there were the blue and red and normal color Legos for the boys, right? So there is some nurture to that aspect. However, recently it's been shown that, yes, there are biological differences between men and women, and we're hardwired differently. It doesn't mean one's better than the other, it's just different. So, I found this picture today. You really can't find anything online. And so I wanted to very basically get at the differences or the sexual dimorphisms in humans. So breasts versus chests, right? That's the obvious one, right? We all know our physiology is different. Men have an Adam's apple. Actually, women have them too. It's just so small, it's not visible. An Adam's apple is formed by the cartilage that wraps the vocal cords. Men have a bigger vocal box because their voice is deeper. So it's usually visible. Women tend to have a heart-shaped face versus square face of a man. Hairy versus not. Men have a lot more hair than women do, and so women start to get older. And then as I'm getting older, I'm noticing, yeah, a little bit different. Fair versus swarthy. So the woman, right? If you look at, I don't know if anybody's read romance novels. I went through a romance novel phase, right? There's always this swashbuckling man, usually dressed like a pirate for some reason, right? Rescuing the fair maiden who's blonde and blue-eyed, and that. And then muscular versus curvy. These seem rather trite, but there are biological bases behind all of these traits. Our brains are different. The brain in a man is about 10% bigger than a woman. That means men have bigger heads. It's true. You can take that any way you want. However, women have more connections between the two hemispheres of the brain. And so you look at the top panel, that's an image of a male brain. And if you look at the connections, they run along the hemispheres. So that's called a box way of thinking about the brain. There's a really humorous video online that a comedian goes through this with the different types of brains in men and women. But men are better at spatial tasks, motor skills. However, women, if you look at the brain from a woman, our connections run across the hemisphere. And what that means is that women tend to use more logic and intuition. Women have better color perception and peripheral vision. However, men have better long distance focus. Why would that be? Hunters. Very good. You guys are great. That's right. We've evolved that way, right? Men had to hunt for the food. The women had to keep an eye on the babies, right, in the homestead. So making sure there aren't predators off to the side. So we've evolved that way. Women smell better. I mean, not, okay. We that came out wrong. Women sense odors more efficiently than men. We actually have more neurons in our olfactory bulb than men. And women have we're better at hearing high frequencies. And why would that be?
Babies crying.
Oh, yeah.
Children.
If you guys have babies, my husband slept through all three of our kids. Every time they cry, I'd kick him and push him, and he'd snore and flop over. I'm like, but it never woke him up. Woke me up every time. Once again, we've evolved for that. Our skeletal makeup is different. Our bones are different, right? Women Women tend to be shorter than men, on average. Males have bigger bones than women, on average. Men have bigger heads, probably for that bigger brain, and longer arms and legs. And I do want to say that just because men have a bigger brain, there is no difference in intellect between the sexes. There's never been any difference found between the sexes. Women have a longer torso, and we have a larger pelvis for delivering those big-headed babies, right? Our skeletal muscle is also different. Men tend to be 40 to 50% more muscular than women. But women are almost as fast as men. Not quite as fast, but almost. Men have a predominance of type 2 fast twitch fibers, which means they're sprinters. They can get up and run quickly. Probably gets back to the hunting, right? You have to sprint, be fast to get your prey. Women, though, rely on a combination of slow and fast twitch fibers. Women are marathon runners. We can run longer, maybe not as fast, but we can outlast the man. These differences also apply to various different pathologies and diseases. So women up at the top, when we talk about cholesterol, sorry, I got out of order. We talk about cholesterol, it's about the same between men and women. However, osteoarthritis, so arthritis and osteoporosis, are greater in men earlier in life, middle age. However, once a woman goes through menopause, women have a higher incidence of osteoarthritis and osteoporosis. Once again, right, our hormones are do have a role in the maintenance of our body and our health. Women tend to sleep less than men. And I don't know if that goes back to the baby thing or not. That wasn't tested. However, oops, I keep hitting this button. We are also different at a very basic level. Our cells in molecular biology are different. So, every cell has a nucleus. The nucleus contains the DNA, which is the genetic makeup of all of us. It's the code that makes us who we are. The DNA is wrapped in chromosomes. We have 23 chromosomes. And between men and women, 22 of them are the same. Sex chromosomes are different. So women have 2X, men have 1X and a Y chromosome. Still pretty similar, though. And this is what the karyotype looks like. So you can see the different chromosomes. The only different chromosomes are the sex chromosomes. And you can see how much shorter that Y chromosome is. So if we talk about DNA content alone, right? And this, when I was a grad student, it's not something that we thought of, size of cells, right? The nucleus in a woman, in all female cells, is bigger because we have more DNA to store than a man does, right? And so there's a mechanical effects. I mean, we're talking one cell, right? So there's not a huge change, but it's large enough to have a mechanical effect on how the cell functions and moves. Oh, there's another picture. The X chromosome has about 1,600 genes. The Y chromosome has 27 genes. Of those 27 genes, only 17 are active. The majority of the genes on the X chromosome are active. And the way we generally think about the sex chromosomes is in relation to our sex, right? Whether we're female or male. However, every cell in our body has either 2X or an X and a Y chromosome. Every cell. So these chromosomes do affect every part of who we are outside of just our sex. So most genes are exactly the same in males and females. They are just read differently because of the sex chromosomes. I'm going to play this video. I have a couple videos because some people say things better than I do. And this is actually, these are all Yale students that were interviewed. And this gets to the idea of we need to
tested. I would not like to take untested medicines.
I would not be comfortable with that. It is important to know how the drug affects women.
No way! That's not good. That's bad.
So 25 out of 25? Wait, ask the question again?
Should all of them be women? Okay. Well, that doesn't make any sense. 2 women? Yeah, you're making that up. Really? Oh, that's sad.
I'd like to see that the science represents both men and women. Just make sure that it's as safe and as effective both in men and women and all different types of people.
There we go. So Ambien was the first drug that really turned scientists around on us, because it turned out that women should take half the dose of Ambien that men do per kilogram body weight. So if you take out differences in body weight, women still metabolize Ambien differently than men. Women were getting up and walking out of their house and driving their cars and sleepwalking, didn't even realize they were doing this stuff because of the Ambien, right? And so that's when the FDA said, well, maybe we should start thinking about some sex differences. There's a lot of drugs out there that do different things in men than in women. I've listed some of them up here. Aspirin. In men, it reduces the risk of heart attack, although in women, the data is not as strong. So I'm not saying it doesn't. My mom takes an aspirin. It's probably a good thing. And it's not hurting her to take it. Alcohol. So alcohol dehydrogenase is what degrades the alcohol in your liver. Women have less alcohol dehydrogenase, it's easy for me to say, which means it takes us longer to get over the effects of alcohol. And so there's several different drugs, right? All of these were tested in men, tested in male animals, tested in male cells. And so 21 years before Ambien was marketed differently for women. It took that long. So aging. Aging affects everybody, right? We all start as an infant. We move through puberty, right? Become young adults, hit middle age. Then once we get to middle age, we get a little bit older. And I don't want to go any further because that's where I am. Right? But it happens to everybody. It's just, but older people and younger people are not the same either. If we talk about pre-pubertal, right, kids versus post-puberty kids, those are very different, but still growing children, right? And so their ability to handle some of these drugs is probably different. And I just want to say that I just showed you that video talking about drugs for women not being tested. Nothing's been tested on kids, right? None of these drugs have been tested on kids. And if your child has a disorder and you go to the doctor, the first thing they tell you is, well, there's been some success with this drug in kids, but it's not FDA approved because it was never tested, right? It's probably something we should think about. We do have an aging population. You can see on the left, it's 1975, 30 years later, the baby boomers are moving up, right? And we're getting older. Well, what does that mean? Well, there are a number of age-related diseases, such as cardiovascular disease, hypertension, and I've got them all listed there, osteoarthritis, osteoporosis, frailty, dementia, eye changes, pretty much every organ system is affected by the aging process. I've put asterisks next to cardiovascular disease and osteoporosis because, as I mentioned before, men have a higher incidence of that in the earlier years. Once women go through menopause, there's a much higher incidence of cardiovascular disease, osteoporosis in women, demonstrating a change in what the change in estrogen is having on the body. So I do study skeletal muscle, and that's my area of expertise at WFIRM. And as we get older, we lose skeletal muscle, we lose mass. It's called sarcopenia. And I really like this picture. That's Arnold Schwarzenegger, right? Big, bulky muscles. And these little old ladies, and I'd really love to know what was going through their mind when that picture was taken, right? Just look at my big muscles. But your young people, young muscle has a really remarkable ability to regenerate after injury. And the truth is, we all injure our muscles every day. Walk up and down the steps, you get these little micro tears in your muscle, especially at the joints where the tendons from the muscle connect to the bone. And we heal it just fine. We don't even know. Even sprains, we tend to heal those. However, more serious injuries our body can't handle. And as we get older, I pick on Arnold a little bit, but he's out there in the public eye, so he's safe. As we get older, we lose that ability to heal, which is why when you're young, you can roll around on the floor and play and wrestle. You can't do that with your grandparents, right? Because you got them on the floor, they probably have a hard time getting back up. We just don't work as well. That's Arnold when he was on testosterone versus Arnold when he was 70. And the truth is, he looks pretty good for a 70-year-old guy. I give him credit for that. But the number of stem cells changes as we get older. And so I'm going to talk about this in regard to skeletal muscle, but really this can apply to almost any organ system. So as we get older, the number of stem cells we have in our tissues decreases, and they don't work as well. Our morphology changes. So remember when I said men are sprinters and women run marathons? Well, for men, that ability to sprint, right, those fast twitch fibers, they switch to slow twitch, which is why you can run fast in your youth, and as you get older, it's harder to get up and move. Once you're up, you're okay, but that whole getting up is tougher. There's decreased vascularization as we get older. There's decreased innervation of the muscle fibers as we get older. We get more collagen and more fat. So myostinatosis is fat in their muscle. So what happens is if an older person injures their muscle, instead of getting muscle tissue back, they get scars and fat, which obviously aren't muscles, so they don't contract. Now let's put age and sex together. Oh, I keep hitting that button when I get a drink. There we go. Put sex and age together, right? The solid lines are for women, the dashed lines are for men. So it's from premenopause or early life to later in life. Women, the red line starts up high, that's estrogen, right? So during our childbearing years, our estrogen is high. As we get older, there's a massive loss of estrogen. In women, FSH, which is the follicular stimulating hormone, it's the hormone that actually matures the follicles in the ovary, goes up and stays up, doesn't come back down. So you've got the switch there. Men undergo a similar type of thing. It's not really called menopause, but their testosterone, if you look at the green line, does decrease, right, over age. So it starts high like estrogen, and as they get older, it goes down. So men have changes in their hormone as well. So we need to take these different components into consideration when we design our experiments. And so some ideas have been put forth, and when I read through this, I was like, duh, yeah, why aren't we doing this already, right? With cells, do we know if our cells are male or female? And quite honestly, I'm a cell biologist, and most of the cells that I use, I'd have to look that up, right? We don't talk about whether the cells are male or female. But they are, right? We talked about chromosome differences. Our cells are male or female. And we should use both of them. How about the age of the donor? Remember I said that older people, their stem cells don't work as well? So if we get stem cells from discarded operating room tissue or OR tissue, probably not as good as stem cells from a younger person. But that's usually what we're left with, is stem cells from discarded OR tissue. For preclinical animal studies, use both sexes of the animals, right? Analyze the results separately. So if you put all of the animals together, analyze your results, you may not see a difference, right? You have to actually look at the men by themselves, the female by themselves, look at them together. And we don't do that. We should. We're starting to do that. We have to. NIH says so. And then consider the sex hormones across aging. And then clinical trials really should have 50% women, unless you're making a drug specifically for women, and maybe you should have 100% women instead of 2. Right? Include older adults, right? Look at the hormone status, which is really easy to do with a blood draw, and independently, once again, assess changes in age versus changes in sex. All right. Now that I've told you all of that, I'm going to talk about tissue engineering and regenerative medicine, right? And how this applies to tissue engineering and regenerative medicine. I put this picture up there because it's kind of an iconic image, right, of the mouse with the ear growing in his back. We actually do that. Mice have very stretchy skin, and if we want to take a tissue and vascularize it, the best place to put it is under the skin. Let it sit and then take it out, and usually the cells are healthier. All right, definitions. What is meant by tissue engineering? What does tissue engineering mean? These aren't trick questions, and there are no wrong answers. So, yeah. So what is engineering, right? Building things. And so if we're building tissue, we're tissue engineering. Very good. So this is the official definition. Aims at the development of biological substitutes that restore, maintain, or improve tissue function. I'd like to think about tissue engineering is making tissue outside of the body to put back into somebody. So it's outside the body. How about regenerative medicine? Anybody?
Doing it from the inside, you're working with the stem cells to
That's exactly right. Any Doctor Who fans? Or is that just me? That's at least one, right? He regenerates, which means make new, or making new. And I like to think about regenerative medicine as happening inside the body. So using stem cells or pharmacological approaches, growth factors, other biological substitutes, to have the body heal itself, right? Regenerative medicine is not a new idea. This is Prometheus. You guys know the story of Prometheus? Yeah. He was Titan. He was brother to Zeus. Prometheus made man out of clay and let them roam the earth. However, he noticed that man was naked. We don't have fur. We don't have claws. We don't have big teeth. We don't have wings, right, to fly away. There's no way of defending ourselves. So he gave man fire, right? Well, fire belonged to his brother Zeus. Zeus wasn't happy, right, that he took fire and gave it to man. So he chained him to a rock, and every night an eagle came and pecked out his liver. And then during the day, his liver grew back. Your liver has the highest regenerative capacity of any tissue in your body. Why is that? What does your liver do? Yeah, that's right. It filters out all the bad stuff that we put into our body, right? All beer or alcohol, drugs, fast food. I'm guilty of that as well. But our liver is designed as the filter. It takes all the toxins out. And so your liver has to be able to regenerate because we're injuring it daily. But the ancient Greeks knew about the regenerative potential of the liver. They knew that. So this is really not a new idea. There are 3 different components to regenerative medicine. And now we're talking about regenerative medicine as an umbrella term. I borrowed this slide. I'm going to change it. But anyways, regenerative medicine, we talk about cell therapies, making new tissues outside the body, like tissue engineering, and medical devices and artificial organs. So hip replacements, right? That's really considered a tissue engineering or regenerative medicine approach, although it's been around a lot longer than the term regenerative medicine. All right. Oh, got stuff. So the why I do what I do section, why should we care? I have to convince my graduate students that this is important. If I want the NIH to give me $5 million, I have to be able to convince a lot of people that what I study is important. Well, here's the truth, right? Every 30 seconds, a patient dies from diseases that can be treated with tissue or organ replacement. If you need an organ transplant, kidney, lung, whatever it might be, you're probably going to die on the waiting list rather than actually get an organ. That's just the truth of it. There's not enough donors to overcome the need. So, but if we could make those, engineer new organs to treat these patients. All right. You guys all know what a newt is, right? Little salamander that lives in the ponds and creeks and, all right, hold on, here we go. So newts are amazing. I mean, as humans, we like to think of ourselves as the top of the pyramid, but we're really not. If I cut a leg off a newt, it grows back within about 3 months to a completely identical limb that it lost, right? If I were to cut my arm off right now, yeah, does anybody know any sort of emergency medicine, right? Because I probably, unless you guys know how to put on a tourniquet, I'm gonna bleed and probably die, make a huge mess. I'm not gonna grow back an arm. My body can't do that, but newts can do that. Other animals can do that. As I said, our body's good at handling little injuries, such as paper cuts, right? We've all had paper cuts, and they go away. However, larger injuries. This woman, she was shot in the face. This gentleman, he's a wounded warrior. Probably stepped on an IED. She lived, underwent many surgeries, and quite honestly, she looks pretty normal for someone shot in the face, but she's not normal, right? Not normal. This is probably a 22 or 23-year-old soldier that lost all of his muscle in the back of his leg. So he's got hopefully a good 50 or 60 years left, right? But he probably can't walk far. He's never gonna run, he's never gonna dance, he's never gonna jump around with his kids. So another thing that we do, we talk about saving lives, but we also want to improve quality of life. It's very important as well. Because what's it worth living 50 or 60 years if your quality is so poor you can't do anything? And so, what do we need to engineer an organ, right? We need cells, obviously. We need a scaffold. So a scaffold is what you use to design the shape, right, of your organ. And then we need a patient to put it in. Ideally, we take cells from the patient, grow it on a scaffold, and then put it back in the patient. We can't really do that yet. And so how does this work? So we use cells, as I said, different biomaterials for the scaffolds, and then we also use chemical and physical factors. And I'm going to talk about each of these. I'm going to spend more time on cells because I'm a cell biologist. I think they're cool, right? A little bit of time on biomaterials, but I'm not a chemical scientist, so don't ask me any difficult questions about that. And I will talk a little bit about chemical and physical factors. So we're going to start with scaffolds. So that's a scaffold, right? We know that's a house. But that house isn't going to provide any protection for the rain, wind, cold. We know that's a house, but it's not really a house yet. That's the same thing that a scaffold does. There's different types of scaffolds that we use. Some are synthetic, which means we make them in a lab. Other scaffolds come from natural sources. Scaffolds have to be able to allow cells to grow, so they've got to be biocompatible. And we don't want scaffolds that are going to harm the patient, right? So if you look at the top, the orange disc, that's a squishy scaffold. And I have determined that squishy should be a scientific term because I don't know how else you would describe it, right? Squishy. What do you think you would use that for? A soft scaffold. Wounds, right? Maybe skin, right, or muscle. That kind of scaffold is used for corneas, for eyes, right? Your eye is kind of squishy. I mean, I'm not suggesting you will poke your eye to find out, but it is. How about a flat scaffold, right? The pig bladder, use that for skin or very thin muscle, right? If you're going to make a blood vessel, you're going to use a tubular scaffold. However, if you're going to make a bone, you need a scaffold that's hard enough to be weight bearing, right? You want to be, especially if it's in the leg or whatever, you want someone to be able to walk on it. So another way that we get scaffolds is using what's called decellularization. So we can take an organ, if we look here, it's liver and kidney. We can take an organ, put soap through it, detergent essentially, soap, and decellularize it. Take all the biological materials off. All that's left is the natural scaffold of whatever that organ was, right? We can put cells back onto that scaffold, presumably healthy cells now, and then have an organ that can be put into a patient. And that's the idea. We're doing this with kidneys in pigs, right? So it's preclinical. Why do we use pigs? Does anybody know why we use pigs in the lab? That's exactly right. Their kidneys are the same size. Their skin, if you burn their skin, it heals like human skin. Rodents don't heal like people. Obviously, rodents have very small kidneys, right? So we use pig kidneys, so that we can approximate the size of a human. We're able to put these, recellularize them, put them back into the pig, right? And get flow, right? So it remains pig. It doesn't last for a very long time. Pigs don't, we anesthetize them, obviously. We don't wake them up because they don't last very long. The problem with this approach is that it's the blood vessels, right? So your blood vessels are made up of endothelial cells on the inside, smooth muscle cells on the outside. Capillaries are one endothelial cell thick. That's it, right? And so when we decellularize the tissue, we lose the capillaries. And if you have cells, if you have blood moving through areas that don't have endothelial cells, you get clots. And so until we can find out a way to fix the capillaries, it's a bit iffy stuff. I just talked about that. The benefits of using a decelled organ is that one, most of the vasculature is there, and two, approximates the size and form of the native organ. So this is showing, so this is a rat liver. It's been decellularized, and they're putting a blue dye into it. And you can see that the blue dye moves out throughout the vasculature of the liver, showing that most of those veins are still pink. So one of the biggest problems facing tissue engineering is perfusion, is being able to get blood to the cells. Cells require blood for oxygen, nutrients, and for waste removal. And if we're going to make big tissues, we have to provide the vehicle for that as the tissue's being engineered or grown. Cells will only survive up to a 3 millimeter cube size. before dying. So oxygen can diffuse 3 millimeters, which is not very big. So we have to, that's a major problem we're facing that has to be overcome. All right, who likes spinach? I love spinach. What does that look like if we look at spinach up close? It looks like a vasculature, right? So this group at in Worcester Polytechnic Institute in Massachusetts has done these really interesting experiments using spinach. So they decellularized spinach. And what they noticed was, you know what? The veins in the spinach pretty much look very similar to the veins in animals. So they decellularized spinach leaves, and then using a red dye, they show that those portals, right, those veins, are still patent, meaning that they're still in shape, and you could use those then as a means of developing a vasculature. Let's see. Yeah. What they did next, and I don't know if you'll be able to see this. I hope it works, yeah. I don't know if you can see that very well. What they did next was they actually put cells on the spinach leaf and showed that cardiomyocytes, which are heart cells, could survive on the leaf, and they started to contract spontaneously on a spinach leaf. So the group that's doing this is actually developing spinach leaves as patches for myocardial infarction, for scar tissue on a heart, right? The idea is to have spinach leaf, right? Stack them up, and then just put them on the heart. And they're still in preclinical research, but it's a pretty interesting idea. All right. What's that? It's not a bell pepper.
It's a cell.
It's 4 cells. That's right. It's a 4-cell stage embryo. What species? Anybody? No, you can't tell. Is it a echinoderm, which is a starfish? And I know that because I took this image off of Google, and that's what it said. Right? We all look the same at the beginning. Every animal on the planet looks the same at the beginning. We all start as a single cell. I thought the 4-cell kind of made a better picture. But this is how we develop. And this actually is one of the reasons why I'm excited to be a cell biologist. Because from those cells, from that single cell, develops every organ system in our body. Right? Everything that we are comes from a single cell. So at one point in time, our bodies made hair, right? Actually, our bodies still make hair to a certain extent. But we grew arms and legs and feet and teeth, right? We knew how to do that. Now our cells have lost the ability to do that, which is good for the most part, because that's how cancer forms, right? When cells start to grow unregulated, we end up with tumors. So we're gonna talk about cells. And as I said, I'm a cell biologist, so I think they're really cool, and I like cartoons. And so if you're a snowman, right, a stem cell is a snowflake, and stem cell parental advice, you can be anything you want when you grow up. Yep. But cells are the fundamental unit of life. They're the smallest body capable of independent reproduction. And that's from Dr. Watson in Molecular Biology of the Gene, a textbook. So one of the questions that we have to ask when we want to use stem cells as therapy is where do we get the cells, right? There's multiple different sources. So embryonic stem cells versus iPS, which are induced pluripotent stem cells, similar to embryonic stem cells, versus adult stem cells. We use allogeneic cells, which would be one person to another. Autologous cells, which would mean a biopsy from me back into me, right? Person to person. However, most banked stem cells, and there are stem cell banks, use cells either from discarded operating room tissue or cadavers, right? Remember what I said, as we get older or diseased, our stem cells don't work as well. So neither one of those are a great source for stem cells, right, for transplant to make new healthy tissue. And so where do we get the cells? And then once we get the cells, how do we get enough cells to use for any sort of therapy? There's three characteristics that define a stem cell. They can repopulate the stem cell pool, they undergo asymmetric division, and they're potent. What that means is that when you injure yourself, your stem cells start to divide. Some of those cells become stem cells, so they go back and repopulate the stem cell pool. Some of them, and that's asymmetric division, some of them differentiate into whatever the final tissue is. That's potency, right? They're found at all stages of life. However, as we age, we lose them. But they're usually good enough to repair our tissue over a lifetime. A little bit of terminology, just to get started. Totipotent stem cells, right? So when we think of embryonic stem cells, they're not totipotent stem cells. Common misconception. Totipotent stem cells have the ability to become the embryo plus all of the extra embryonic tissue, such as the placenta and the amnion. Pluripotent stem cells, those, when we think about embryonic stem cells, those are pluripotent stem cells. Those are cells that can become any tissue in the embryo. Multipotent stem cells, these are postnatal stem cells that can give rise to any of the cell types of the germ layers. And then we have unipotent stem cells. And these are the adult stem cells, tissue-specific stem cells. And quite honestly, it's the multipotent and the unipotent stem cells that are used most for in research and in the clinic. So quickly, embryonic stem cells, these are taken from blastocysts early on. And all of the embryonic stem cells that are used in research are derived from discarded in vitro fertilization eggs. All right, so it's a misconception to think we get them from aborted fetuses. We don't. They're all from, when a woman undergoes IVF, she has many eggs fertilized. The ones that aren't used go into a liquid nitrogen freezer. At some point, that woman says, I don't want these eggs, right? And then they're discarded. Some of those eggs, if the family agrees, can be used, and embryonic stem cells can be isolated. The problem with embryonic stem cells, one, they form teratomas. I did not put a picture of teratoma up here. You guys can look up teratomas on your own. All tumors are bad, but teratomas are like the nightmare of tumors, okay? These have hair and teeth. Sometimes they get them in the eye. Remember, because these cells can form all different tissues of the body. And then, once again, there are several ethical considerations. So a lot of research is actually being done with multipotent stem cells. These are the mesenchymal stem cells. You might have heard of mesenchymal stem cells. So they're non-fetal sources. And they're already being used in clinical trials. And then adult stem cells, which, as I said, these are the stem cells that I use. I use stem cells from muscle, so they're adult stem cells. And they're lineage restricted. They can only become one thing. All right. Before we finish stem cells, I have to talk about my favorite creature. Now this guy, I didn't know anything about this guy until this summer, right? And now he's amazing. This is a planaria. Very simple. They get about to the size of your thumbnail. They're small, found in streams, freshwater streams and lakes. They have a head, sort of. They have two eye spots that sense light and dark. They have a tail. I'm going to show you this video because I think they're neat. Okay.
Thanks to CuriosityStream for supporting PBS Digital Studios.
This goofy little guy is called a planarian. Sure, it's just a flatworm at the bottom of a pond, but it has a very special superpower, one that scientists would love to harness. To show you, well, it's gonna get a little bit slasher movie here. Okay, Don't worry. It's going to be okay. Seriously. I promise. It doesn't even hurt. That would be curtains for most organisms. I mean, this piece here is just a chunk with no head and no tail. But watch. You can see under a microscope that overnight its wound heals closed. Okay, maybe we could do that, more slowly of course. But then it starts to regenerate, growing new tissue. It's that white part, called the blastema. In a week, see those tiny little spots? They're new eyes grown from scratch. But the planarian, can I call it that yet? It still kind of looks like a blob. By day 12, it's starting to look like a proper planarian. It's got a head, an entirely new one.
We'll do it again. Planaria are really cool, okay? You can take one small planarian and cut it into 278 pieces and get 278 worms, right? You're probably wondering who did that to figure that out, right? Somebody back in the 17th century figured that out. And if you can imagine, right, what they had to use a microscope back in, late 1600s was not much. And so what this guy did was take a planarian, cut it into multiple pieces, 278, and then every day drew those pieces, right? And see, and documented the regeneration. And you can actually find that online. That's how I know that. I don't know what happens if you do 279. I don't know if they explode or what, but 278, that's all you got. Why can they do that? Why can planaria do that?
Help stem cells.
They are filled with stem cells. It's a little hard to see here, but this guy at the top, all that green, that's stem cells, right? He's got stem cells from the top all the way to the bottom. There's one place that you can cut a planaria to a piece that won't regenerate, and that's above the eyes. You can't see that here either, but right above the eyes, the eye spots, there are no stem cells. So even though the planaria itself would grow that portion back, the little piece won't grow in the planaria. In my kitchen, I have an aquarium filled with planaria, because I did this experiment with high school students who cut them into 3 or 4 pieces and literally quadrupled the number of planaria that I started with. And then I couldn't, I don't know. I thought they were neat, so I kept them. Unfortunately, my daughter's at college because she thought it was disgusting. So stem cells. Stem cells are important, right? And I kind of mentioned this before, but we need to consider sex when we talk about stem cells. Male stem cells, female stem cells. Remember, different DNA content. Nucleus is larger in one than the other, and we don't do this. We still are not really doing this. We take whatever cells are available, and most of us cell biologists, me included unfortunately, up to this point haven't really considered whether they're male or female. But if you take a male stem cell, put it into a female patient, you now have an XY chromosome, right, responding to the environment of an XX person, right? The outside stimuli. And same vice versa. So does it have an effect? Probably. Is it enough to make a difference? Nobody knows. Nobody's really done the experiments to see if that makes a difference. However, I can tell you, and I'm not going to go through these slides completely, estrogens, right? These are all the different things that estrogens do on different cell types, right? So if you take an XY cell that's not used to high estrogen, put it into a female. Vice versa, if you take an XX cell and put it into an environment with high testosterone, how's it going to react? We don't know. Cells also talk to each other, right? cells don't live in isolation in our body. They live in tissues and organs and so forth and so on. They talk to each other. That's what this diagram is showing. They have signals that tell itself what to do, tell neighbors what to do. They have autocrine paracrine effects. They can even secrete factors that tell different organs and tissues what to do. So when we're trying to engineer a tissue outside the body, we have to replicate that somehow. And that's quite difficult. So back to planaria, because I really like planaria. What happens if you disrupt the signaling pathways, right? So the top left-hand corner, what they did was they turned off Wnt signaling, which is pathway. And now this planaria has like a dozen heads, right? If they overexpress it, now it's got too many tails, not a head, right? So these pathways are very important. And then regenerative rehabilitation. And so this is the newest hot thing in regenerative medicine. And it's one of those things where you go, man, why didn't I think of that term, right? Because now there's funding for regenerative rehabilitation and all these other things. But really what it says is that when we make tissues and organs, we have to exercise them, right? So baby in the womb is never still. It's constantly moving, constantly exercising those muscles, the joints. And so to have an effective tissue outside the body, we have to replicate that. And we have bioreactors to do that. And these are different muscle bioreactors. This is a really old one from W-Firm. Basically what it does is you put your cells on some sort of scaffold and you stretch it really slowly before you put it in an animal, right? And so this leaves us here. I think I have 2 slides left. This leaves us here. Where are we today with any of this, right? Well, as I said, perfusion's a problem. So flat, we're doing skin, right? Bone, we're actually making some progress with because it's mostly avascular. So, same with cartilage. Flat scaffold skin, squishy scaffolds because oxygen can diffuse through squishy scaffolds. Blood vessels is basically flat, wrapped into a tube. Bladder. So Dr. Atala, my boss, was the first surgeon to put a tissue-engineered organ into a patient, and it was a bladder. And if you think about it, bladder is a flat sheet kind of rolled up, right? It's like a balloon. It's still thin. So when they did that, they didn't have to worry about trying to get blood vessels integrated as they were developing the bladder. Then we get to the solid organs, right? Kidneys, liver, muscle, heart. We've got a lot of work to do there. These are some of the barriers, and I've talked about most of these. Finding cells, expanding cells, vasculature, tissue architecture, scientific and technical scale-up. So say we can make these, how do we scale it up so that it can be used consistently in patients, right? And we're just starting to look at that now at W-Firm in some of our manufacturing initiatives. There is some work. This is a trachea. It was put into a patient, and I think it was in Sweden, could be wrong, but the paper's up there. Once I said, Dr. Atala with the bladder, heart valves, right? And then skin. So these are actually tissues that are being used in the clinic. And I'm going to stop there, because I think I've talked enough. And I will answer any questions. I could really talk all day, but I'm pretty sure you guys don't want to stay here all night listening to me.
Anybody have any questions?
And it can be about anything. If you want to ask me about muscle, I didn't show a lot of my data because, well, my interest is really in sex and aging differences. And the truth is I don't have a lot of money to be researching that yet. But I'm working on that.
So he's got the scaffolding. You know, he's got the scaffolding, and you're going to put the tissue on it. So what does that mean for the tissue that you have to get now for a transplant?
For the tissue. Right, so if we use cells, say we're making a kidney, right, and we use cells for a vein, we're going to run into the same graft-versus-host disease that the patient has to deal with, which is why using patient's own cells would be ideal. However, usually the patient's own cells are diseased or injured. But there's a lot of genetic engineering research that's going on to try to fix those cells. But maybe we can take cells out, fix them, and from that.
They're still have a problem.
You're still going to have a problem. Yep. Yep. Still going to have a problem. I thought there was there a question?
Do you have any reference literature, research on the use of stem cells or the application of stem cells related to prostate cancer?
Prostate cancer. I haven't, excuse me, my allergies decided to work just back up today. I haven't seen any specifically for that type of cancer, but that doesn't mean it's not out there. I can't answer that question.
This might be a bit of a weird question, but back when you were talking about the changes in how they want you to do the research or drugs, I would think that there'd be quite a bit of space for also going back and just doing some of the research that was done on men and redoing it on women, so we actually have the full data set that we should have.
Yeah, you're absolutely right. That's not a weird question at all.
Back a few years wrote some.
Write grants, they want us to do both sexes, right? So do we really have to do the men again if we've already tested all these in men? And the other point to that is it's really a new field of research. So I showed you a video from Yale, which has a women's health research department. And there are a couple universities across the country that are specifically geared towards women's health research. And that's not to discount men, but it's to catch women up, right? And some of these drugs where men are. And so that's really it's not done everywhere yet, but it's becoming more common to see that. So.
And that's one of the things that's actually done in that particular branch of research?
It's starting to be done, right?
Oh, I know where I want to look at then.
Excellent, there you go. Wonderful.
Anybody else?
Dr. Criswell, you mentioned Dr. Atala's bladder.
Yes.
And I know that when we've seen Dr. Atala present, he'll present the person who actually received that bladder. Could you give us an update on that?
Yeah, so I guess I haven't gotten the real recent update, but he still has a bladder. So Luke had spina bifida, and he had to wear a colostomy bag. And as you can imagine, when you're a kid, having a colostomy bag is really not a pleasant thing, right? You want to go play outside, you want to run around, wrestle, have friends, and you can't really do that so much with a colostomy bag. And so Luke was one of the first, I think he was the first patient to receive the bladder, or one of the first patients to receive this tissue-injured bladder. And the nice thing about it is that they use the patient's own cells, and the bladder grows as the patient gets older. And so Luke is, he's got to be out of college now, it's been that long, but he still has his bladder.
So Dr. Criswell, I have the opportunity of thanking you on behalf of the SciTech lecture series. I'm Nancy Johnston with the North Carolina Biotech Center, so it's good to meet you. And I just want to tell you guys that to sit here and see the excitement of the promise of tomorrow, this is to have this expertise here, and for you to be engaging the way that you are is really exciting, because what you're hearing today is the future of tomorrow in medical interventions, and it's happening right here in Winston-Salem in the Piedmont Triad of North Carolina. So we are super excited to have your expertise. We don't take that lightly, but what I'm most excited about is the wonderful educator that you are and how committed you are to the passion, because this is hard work and it's long work, and it's great to have your talent here. So I will tell you, just in the context of the state of North Carolina, we do have several hundred companies. You talked about the research and development, and then the realities are this is translational medicine, so this isn't just an idea. This is something that's moving forward that's really going to make a difference for humankind.
and probably your children's children may benefit, or you never know, you may benefit. And in this area, so we all live here, we work here, we go to school here. We have several dozen companies working in this space, whether it's around 3D printing, so your convergence with IT and healthcare, or whether it's around even just clinical trials. Look up Body on a Chip. I think you'll be amazed at what you read, and you'll also be amazed that that innovation is coming out of this community and your work and others. So I want to recognize my great partner, Russ Reed. Because of the partnership, we've been afforded to partner on the SciTech. So I think Russ wants to present something to you. But thank you again for your time, and thank you everyone for your participation.
Thanks, guys.
If any of you have questions, you can find me on the WFirm website, and you can send me an email. I'd be more than happy to answer any questions you might have. If you're like me, I always think of things like an hour later. So,
Dr. Criswell, I know you have a PhD, but this is something you don't have, which is a nice certificate signed from the administration here, from both the National Center and also from Forsyth Technical Community College. So thank you very much for your preparation. And by the way, I think I mentioned it at the outset, but Dr. Criswell has been a very faithful lecturer at something we call the Biosciences Industry Fellows Program, which is an NSF grant which we have, and she's been with us 3 or 4 years now. Thank you.
yeah. Well, thank you so much. I really appreciate it. It's been great.
Thank you.
But that shows your passion. Thank you.
The planarian, or we've been doing it in I mean, truth is, I've heard of planarians since high school. We've been doing it in the summer. I never actually. How did I not do this before?
It's great, so we'll be putting planarian
There, I mean, it is good. What they can do. And so it's just figuring out how they can activate this program and try to
It's so weird. It's amazing what they're doing with the kidney now. It's so complicated.
All right, Russ, I'll be in the morning to send everybody the paperwork.
Thank you. All over.
Okay, I'll see you in the morning.
We try to have our eyes open.
So let's take multiple. Now let's recommend.
Yes, of course. I had a blast. And teachers, talking to teachers is so different than talking to other people, you know, because they're just as excited. I have 3 teenagers for the next 3 weeks. So my daughter is almost 20, and then my son is 16.
Any scientists?
My daughter thinks it's gross, but she's going to be a political scientist. She wants to be a politician. But she's actually quite my middle child wants to be a meteorologist, which she's 20.
I just
My house was an anthropologist.
Wow.
So
let me.
not my kind of science, but
As soon as I get a sense of.
Nice to meet you. And Dr. Criswell, that was great. I teach cell culture here at Forsyth Tech, and I was wondering, we only have 4 students. Would there ever be a chance of maybe a field trip?
To W? We do that all the time.
Really?
Yeah, we have
that
classes
would be
and
great.
students coming all the time.
We were talking about cell flow cytometry, so I got Flo John's email address, and but I just wanted to know, do you think if that
Oh, yeah,
might be
yeah,
something. Could I
definitely.
send you an email?
Yeah, definitely,
Okay.
and I'll forward it on to the woman who actually.
Great,
sets
because
it up.
the 4 students I have, they want
Oh,
to do
yeah.
tissue culture, they
We,
want to do
uh,
cell culture, so.
I mean, almost daily we have tours going.
Oh, wow, okay. Okay. Well, thank you. Oh, yeah. No. Oh, okay. No, I gotta get in on this.
It's one thing to see it on slide.
Exactly.
But to see it.
See the valve.
Moving, yeah.
Absolutely.